A NASA project called Resilient Autonomy has developed autonomous software to help prevent airplane crashes. This software is called the Expandable Variable Autonomy Architecture, or EVAA, which stems from the Automatic Ground Collision Avoidance System, or AutoGCAS.
This technology started off 35 years ago on the FTF-16, only a few hundred feet away from us right now. That was the first aircraft with a high-performance aircraft with a digital flight control system, and we started to bring a lot of automation onto it. We quickly found that automated safety was a critical component just even to flight test it. Over the next 25 years, we worked towards an automatic ground collision avoidance system and eventually got it fielded in the F-16 fleet.
Okay, gonna roll inverted.
The AutoGCAS system takes control of an aircraft from the pilot at the last possible moment to avoid an imminent ground collision.
That's all automatic.
Today, it's saved up to 11 lives out there in the fleet. But that technology was focused on supporting fighters, and it didn't scale well to other platforms.
The team changed the algorithms used in the F-16 version of AutoGCAS to make them suitable for non-fighter aircraft, like Cessnas or remotely piloted aircraft.
We've created a software architecture that can be expanded to support any mission or platform.
Mode on.
It can support variable autonomy in the fact that
Fly up left.
it can be safety augmentation and warn a pilot, to all the way to a fully unpiloted aircraft that doesn't even have a pilot in the loop. The intent is to create a software architecture that can easily be adapted to any form of mission or platform or autonomy level you want.
See if it'll pick right or left here.
This version includes functions to prevent smaller airplanes from diving into a canyon, into the side of a mountain, or into the ground in the event of an emergency by avoiding obstacles and guiding the plane to a safe landing area.
It draws upon multiple systems, multiple sensors, and it leverages hopping from one system to the next, prioritizing different safety elements or the mission. So we're emphasizing that timing element of going from one thing on to the next in rapid succession.
Now we will be in altitude hold mode, slightly different than we were before. That is going to fly us through that notch over this very complex wind turbine farm. All right, now we just picked up a detection of a king air at our 6 o'clock high.
An element called the moral compass helps the software decide which moves to make by switching control to the highest priority task based on weighing the odds of safety.
The moral compass is at the heart of this rapid switching.
Okay, you can see it's triggered into the yellow mode there, well clear. So it's in a dive. You can see we've got basically a fence or a wall of these wind turbines in front of us, and we're just cresting over the top of a line of them behind us. But we're still in well clear mode. It doesn't yet care about the wind turbines, so we're descending out of the way of that traffic that's almost directly overhead us now on the approach. We're getting closer to those wind turbines. Okay, now GCAS is taking over, climbing right turn, an aggressive turn to the right. Now it detects it's fairly close to the aircraft, so it is doing an aggressive left ACAS turn, climbing away right on the edge of these wind turbine obstacles. And now it's back into well clear.
We're trying to deconflict the hazards temporally, separate them in time, and then quickly resolve each individual one so that now we can switch from one to the next, to the next, to the next. So we bring this metadata, processed metadata, onto the aircraft, whether it's terrain or obstacles or risk of landing. And that gives our algorithms a strategic vision of how it needs to execute things. So we can then trade these and decide this is the most important thing.
To increase aviation safety and decrease the number of crashes, the DoD, the FAA, and other groups such as the Alaska Bush Pilot community are looking into how this software could be integrated into a variety of aircraft in the future.
General aviation, especially the Bush Pilot community, has a very challenging task to go out there and fly in a very rough environment. And they see higher loss rates This technology could prevent that.
The EVAA software is being managed under the NASA Armstrong Flight Research Center Technology Transfer Office. Future availability and capability enhancements will be managed by an extended potential collaboration of NASA, the DoD, and the FAA.
Clear to climb the 18,000.
Other NASA projects, such as Advanced Air Mobility, are looking at potential use cases of EVAA as they investigate how to help the FAA integrate air taxis, cargo delivery, or small package delivery vehicles into the national airspace.